half past 10 in Moscow and 3:30 p.m. in Beijing. I'm very happy to welcome our today's speaker. Bai Sheng will tell us about satellite constructions and canonical decompositions of Brunnian links. So let's welcome.
Thank you for the invitation. My title is Satellite Constructions and Canonical Decomposition or Geometric Decomposition for Brunnian links. This is a joint work with Jiming Ma. This paper is to appear in JKTR. Satellite constructions and geometric classifications of Brunnian links, and in this paper and in my talk, the following paper will be frequently cited, which is written by Badney, JSJ decompositions of knot and link complements in F3. Yeah. Okay, now we start.
By the way, I think we should invite Badney to our seminars. So if you are in contact, it would be great.
Oh, it would be great. Yeah. I don't meet him now. Excuse me, do you meet Badney?
No, unfortunately, no.
Okay. For my contents, here is there are three main parts. Yeah. What we mainly focus on is actually the satellite operations on Brunnian links, and actually satellite operations will give beautiful results on Brunnian links. For the first step, step, we will define two special satellite operations, both of which can construct infinitely many distinct Brunnian links from almost every Brunnian link. Yeah. This is the construction direction. Yeah. Then the second step, we will discuss the decomposition direction using satellite operations. We will give a geometric classification theorem for Brunnian links and characterize the companionship graph, which is defined by Badney in his frequently cited paper. And then we will also develop a canonical geometric decomposition. Yeah, which is simpler than the JSJ decomposition for Brunnian links. Yeah, the main result in the second part would be the following. Yeah, we should conclude that the building blocks of Brunnian links turn out to be whether the I call it a hopeful n links here, but actually it's usually called 2 to n torus links. Yeah, 2 to n torus links. And this is the suffered fiber case. The second case is the hyperbolic Brunnian links, of course. And the second part is the hyperbolic Brunnian links in unlinked complements. This object may be easy to imagine, yeah, by the words, but I will also define it rigorously later. Yeah, but the third step, what leads to the third step? Yes, the third case leads to the third step because we are not satisfied that such thing. Hyper-Brunnian links in unlinked complements to be a kind of building blocks of Brunnian links in S3. So we will define an operation to reduce a Brunnian link in an unlinked complements into a new Brunnian link in S3. Yeah, and then we have some basic investigation on it, and we will point out some simple phenomena concerning this operation. Yeah, on tying. It's called untie. Yeah. Now we start from the definition of Brunnian links. What is a Brunnian link? Yeah. A link L of n components in S3 is Brunnian if it satisfies the following properties. Firstly, we call it a subtrivial or abbreviate, which can be abbreviated as ST. Yeah. that is, every sublink with n minus 1 components is trivial. Yeah. The second property is a non-trivial property, or which can be abbreviated as NT. Yeah. That is, this link itself is non-trivial. Yeah. So the Brunnian links are those links which are almost trivial. Yeah. Then I want to say that Brunnian links are important. Yeah. Why Brunnian links are worth to study? Yeah. Because for a link, yeah, given any link, the non-trivial sublinks with the least number of components, yeah, are either knots if it has only one component, or Brunnian links if it has more than one component. Yeah. Thirdly, I want to say that I want to discuss the following question. Yeah. Why can Brunnian links be thoroughly understood based on some known knowledge, or say basic knowledge? Yeah. At least compared with the very complex, complicated object knots. Yeah. Why and what should be the most natural tool to study Brunnian links? Yeah. The nature of Brunnian links is that each component is the boundary of an embedding disk. Yeah. So we may handle the basic nature of Brunnian links without involving content and the dynamics of knots. Yeah. And the most basic tool then should be those spanning disks. Yeah, we can choose the disks which bound each component to be the basic tool to study Brunnian links. Okay. This page is just a brief introduction of Brunnian links. Yeah. Now we move on to the first part of my talk. Satellite operations for Brunnian links, or say satellite constructions for Brunnian links. We will define, we will give a new name to two special kind of satellite operations for Brunnian links. Yeah, and investigate their properties. The topic sentence in the first part is that one can construct infinitely many distinct Brunnian links by satellite sum. This would be defined later from every Brunnian link, and by satellite tie, this will define later. Yeah, from almost every Brunnian link. Yeah. We will give a notion which will be very, very frequently used in my talk. We should say a torus is knotted or unknotted. Yeah, in my talk. Sorry.
Well, I write some comments in the chat line, but I don't say anything.
Oh. Sorry. Well.
Well, okay, just go on. Thank you.
Oh. But there is some problems in my Zoom here, I think.
Yeah.
Let me have a look at. Okay. Now I go on. Yeah. By a classical theorem due to Alexander, yeah, every smooth torus in S3 bounds at least one solid torus, yeah, in S3. So we can just simply ignore this submanifold of S3. We just use the term knotted or unknotted in S3. Yeah, a smooth torus in S3 is knotted if it bounds only one solid torus in S3. Yeah. Otherwise, it is unknotted. It means that if a torus bounds if both sides of the torus is a solid torus, yeah, then such a torus will be called unknotted. Yeah, we will frequently use these two definitions in my talk. Yeah, I think it is clear now. Okay, now we define satellite sum. So let's firstly have a look at a picture like this, like here. Yeah. Now we state the rigorous definition. Yeah. Let L and L prime be links in S, be two links in S3, and C is a component of L, and C prime is a component of L prime, which are all oriented unknotted components. Yeah. Then and homeomorphism, a smooth homeomorphism, H from S3 minus the interior of a regular neighborhood of C prime to the regular neighborhood of C. Yeah. I mean that consider link L and an unknotted component C, a link L prime and an unknotted component C prime. Yeah. We consider a regular neighborhood of C here. And we also dig out a regular neighborhood of C prime for L prime. And then the complement space of NC prime is also a solid torus. Yeah. Then we use a homeomorphism to map this solid torus into this solid torus to seal into it. Yeah. Such a homeomorphism maps the oriented meridian of NC prime to the oriented oriented longitude of NC, and maps the oriented longitude of NC prime to the oriented meridian of NC. Yeah. Here the N means the regular neighborhood. Yeah. Then we will get a new link. Such link is like this. For L, we have L minus C. That is all of the rest components. And L prime minus C prime, which is mapped by H into this solid torus. Yeah. The union of them, the discrete union of them, is the satellite sum of LC and LC L prime C prime. And we will denote it as L with respect to C plus C prime L prime. Yeah. We call it a satellite sum because the definition is actually symmetric to both to L and L prime. Yeah. This part, yeah, this part is actually give a canonical way to make the definition uniquely well defined. Yeah. Now let's have a look at an example. Yeah. Okay. What we have defined is the satellite sum of two links. Yeah. Now we can make a satellite sum for more links. Yeah. How would that form? Actually, that would form a tree structure. Yeah, just like this example. Please have a look at this figure. There are 5 Brunnian links on the left. Then we can make a satellite sum of them. Yeah, which of course expressed in terms of the links and the removed components. Yeah, we label the links here, and we also label some components here. Yeah, and we will make such an satellite sum. Yeah, this is a tree structure. Yeah, and then the result would be like here, like this. This is the resulted link. Let's have a look. The first in the central here, in the center there is a L5, this thing, and we use C12 and C52. C52 is this component. C12 is this component. We make a satellite sum for this L2 and L5. Then there we will get a white-hat double. Yeah. For L3, similar. For L4, similar. Yeah. And then we make a satellite sum of with one more white-light link here. So here actually we actually get white double of white-hat double of the original component. Yeah, so the resultant link is this one. Yeah. This is an example. Yeah. Now let's look at one more example, which is a famous link called the Milner link. Milner link, for example, we have, if there are 7 components, we will call this, we will denote this link as M7. Yeah. I have drawn the torus here. Yeah. From this torus, we can see that M7 is actually the satellite sum of M4 and M5. 1, 2, 3, 4. Yeah. And 1, 2, 3, 4, 5. Yeah. We can decompose it step by step, and as a result, we have the following. Yeah. The Milner link Mn is the satellite sum of n-2 Brunnian rings. Yeah. If a Milner link have only 3 components, it is just a Brunnian ring. Yeah. And the tree structure is just a path with n-2 vertices and n-3 edges. Yeah. I think now the definition of satellite sum is clear. Yeah, now then we move on to some properties of satellite sum when restricted to Brunnian links. Yeah. If restricted to Brunnian links, we have good results on satellite sum. Please see this theorem. Firstly, Brunnian property is preserved by satellite sum. That is, the satellite sum of 2 Brunnian links is a Brunnian link. Yeah. Conversely, we have the second clause, which states that if a torus T in S3 splits a Brunnian link L, split means both sides of T has some components of L, then T must be incompressible, and L will be decomposed by T as a satellite sum of 2 Brunnian links. Yeah. Each splitting torus split a Brunnian link into 2 Brunnian links. Yeah, this is the converse direction. We have such a result. Yeah. For example, everyone is a Brunnian link, so the resulted one is a Brunnian link. Yeah. This is the for the first class. Yeah, the second class consider the converse direction. It is also true. Yeah. And we please note that hop link is the identity in the satellite sum operation, which means that the satellite sum of a hop link of a hop link and any other link will be that link itself. Yeah. Then we will define what is called a satellite prime. I will just call it S prime. Yeah. A Brunnian link is S prime if it is not hop link and there is no essential unknotted torus in its complement space. Yeah. Briefly speaking, yeah, a Brunnian link is S prime if and only if this Brunnian link is not a satellite sum. Yeah. It cannot be decomposed into the satellite sum of 2 Brunnian links. Yeah. This is the term S prime. Yeah. As we have considered the construction, the composition direction, yeah, for satellite sum, we now consider the converse direction, the decomposition of Brunnian links. Can we decompose Brunnian links into S prime factors? Yeah. Does such decomposition has existence and uniqueness? Yeah. The answer is yes. Please see the following proposition. Yeah. Every Brunnian link except the trivial one hop link can be represented uniquely as the S sum as the satellite sum of S prime Brunnian links with respect to the pairs of removed components. Yeah. In other words, the satellite sum tree structures expressed in terms of S prime Brunnian links correspond bijectively to Brunnian links, except the trivial one Hopf link. Yeah. Briefly speaking, satellite sum decomposition for Brunnian links has existence and uniqueness. Yeah. It does not hold for general links. Yeah. Now we move on the second construction called satellite tie. Yeah. Here we can have a look at an easiest, the simplest construction of satellite tie. Yeah. If we roughly explain here, actually we first have a Brunnian link in a solid torus, and we use a knot, use a companion knot, yeah, to tie this solid torus. Then we get a new link like this. Yeah. Now we give the rigorous definition here. Yeah. Let L0 disjoint union with Ln be a link in S3, where Ln is an n-component oriented unlink. Yeah. And let Ki for I from 1 to n be non-trivial null types. Yeah. Now let such space S3 minus the interior of a regular neighborhood of this unlinked Ln. Yeah, we denote it as UN. Yeah, it is actually a unlinked complement. In other words, the complement space of an unlink. Yeah, we should embed this thing into S3 or re-embed this thing into S3. Yeah, let H be such an orientation preserving embedding. Yeah, so that for this embedding, the complement space, that is S3 minus the image HUN, will be a disjoint union of n not complement space. Yeah, so each connected component is S3 minus n nki. Yeah, here is actually not complement space. Yeah, and here H partial n ci corresponds to partial n ki. That means the we make a we make a correspondence between ci and ki. Yeah. And we will make this definition uniquely well defined. So there is one more sentence. And the oriented meridian of NCI maps to the oriented non-homologous curve in S3 minus HUN, corresponding to the oriented longitude of NKI. Yeah, just a standard choice. Yeah, to make the definition uniquely well defined. Yeah, then the result link, the image of L0 under H is a satellite tie denoted as L0, this link in an unlinked complement. This is an unlinked complement space, this thing, which is a subspace of S3. Yeah, and use such knot types. One each corresponds to NCI. Yeah, and we use them to tie it, and the result link is L. Yeah, this is the notation. Yeah, and we can.
Excuse me.
Excuse me.
Yes. I have a very silly question. You wrote S3 minus HUN is homomorphic to union.
A disjoint union, yeah.
Disjoint union.
Yeah, disjoint union of several not complement space.
I see. No, okay. I'm a little bit confused.
For example, in this example, okay, I just I will just give the explain this example.
Okay,
now.
okay. I will read. Yeah.
Okay. We call this part, in this definition, satellite pattern, or abbreviated as S pattern of the resulting link L. Yeah. For example, U1, is a solid torus. I mean, the complement space of an unknot is a solid torus, right? Yeah. And the satellite tie like this K is a trefoil. This K is a trefoil. And this is a pattern. The pattern is here. Which is the so-called C1? It's actually here. Yeah, this is C1. And this solid torus is the complement of the unknot C1. And we embed this solid torus using this knot type into S3. Then the result will be like this.
Okay.
I mean C1, this unknot C1 is the core of the complement space, this thing, So this solid torus is S3 minus NC1, this red solid torus. And we embed it into S3 to make the complement space not an unknot, but the complement space of a trefoil. Then the result will be like this. Okay.
Thank you.
It is easy to see that varying the knot type of K here will give infinitely many distinct Brunnians. Oh, the result link is Brunnian, and we will say it now. We will say it now. This will be our main result for the satellite tie construction for Brunnian links. But firstly, we need some basic definitions. These definitions are easy. I just read them. In a three-manifold, a link is a disjoint union of simple closed curves. A link is trivial if it is the boundary of mutually disjoint disks. A link is Brunnian if it has more than one component and all of its proper sublinks are trivial and it itself is non-trivial. Three-manifold UN is an n-component unlinked complement. Unlinked complement if it is homeomorphic to a complement space of an unlink. To S3 minus interior of a regular neighborhood of Ln, where Ln is an n-component unlink for n is positive. When n is positive. Now, so using this definition, so we give an example. For example, if L is a Brunnian link in S3, and L prime is a proper sublink of L with more than one component, then L prime is a Brunnian link in the unlinked complement space, S3 minus the interior of L minus L prime. L is a Brunnian link in S3. L prime is a proper sublink. Then L prime is a Brunnian link in the complement of the rest component of L. The proof is trivial. With this clearly defined definitions, we state our theorem for a satellite tie of Brunnian links. Suppose L is a satellite tie of this pattern. that is this pattern tied by those knots, by those knot types gives L. Yeah. Then our basic result is that L0 is Brunnian in this unlinked complement UN, if and only if the tied L is Brunnian in S3. Yeah. Yeah, this is a construction part. Yeah. For example, this two-component link is Brunnian in the solid torus. Then this black part is Brunnian in S3. Yeah. Okay. Then we will also consider the converse direction. Yeah, the decomposition direction. Yeah. The result is that every knotted essential torus in a complement of a Brunnian link bounds the whole link in the solid torus side. Yeah, that means every knotted essential torus cannot split a Brunnian link. Yeah, the whole Brunnian link can only be in the solid torus side of the knotted torus, not of the knotted essential torus. Yeah. I'm not sure this definition is necessary. Okay.
Excuse me.
Please.
Thank you. I want to read theorem again.
Oh, okay.
Oh, thank you. Thank you.
This is a construction direction. This is a decomposition direction. Yeah. Okay, well, let's give the definition of geometrically essential. Yeah. We are familiar with the definition of geometrically essential in solid torus. Yeah, we just generalize it, generalize the definition to unlinked complement. Yeah, a compact set K in an unlinked complement space. In an unlinked complement, U is geometrically essential if and only if the boundary of U is incompressible in U minus K. Yeah. In other words, if and only if for each I, Ci fails to bound a disk, avoiding K and all of the other Cj. Yeah. This is called geometrically essential. Yeah, the compact set is geometrically essential. Yeah. What we want to say is that we see the following. Given a geometrically essential Brunnian link in an unlinked complement, yeah, I mean L0 is a Brunnian link in this UN, yeah, and L0 is geometrically essential in UN. One can always construct infinitely many distinct Brunnian links. Yeah, use such satellite type by just taking each Ki to be every non-trivial knot type. Yeah. This is also a simplest example. Yeah, you can replace a trivial to be any other knot type, and you will give, and it will give infinitely many distinct new Brunnian links. Yeah. Now we move on to some deeper investigation for decomposition for a satellite type for Brunnian links. The converse direction compared with the construction. Yeah. Firstly, a Brunnian link is called untied if there is no essential knotted torus in its complement space. Yeah. In other words, a Brunnian link is untied if it is not a non-trivial satellite type. Yeah. So if if a Brunnian link is a non-trivial satellite tie, yeah, we may find a companion knot, yeah, knotted essential, sorry, a companion torus, a knotted essential torus, and which can show that this Brunnian link is a satellite tie. Yeah. So we will investigate that. We will ask that does such satellite tie decomposition has have existence or uniqueness? Yeah. The result is a bit more complicated compared with the satellite sum. Yeah. Firstly we need to define a special kind of companion torus called a phi companion. Roughly speaking, informally, a phi companion is an innermost knotted essential torus in a link complement. Yeah. The rigorous definition is here. For a link, a knotted essential torus T0 in the link complement space is a phi companion if there is no knotted essential torus T, so that T is contained in the solid torus bounded by T0 in S3. Yeah. In other words, T is inner than T0. Yeah. And T also bounds a solid torus in V0, and T is not parallel to T0. Yeah. Informally, a phi companion is just an innermost knotted solid torus in a link complement. Yeah. Our result for the uniqueness and existence of satellite tie decomposition for Brunnian link is as follows. Yeah. For a Brunnian link, the maximal collection of phi companions with no isotopic pair is finite, and the tori are destroyed after isotopy. Yeah. Briefly speaking, the collection of phi companions has existence and uniqueness. Yeah. Such a result does not hold for general links, actually. If you are familiar with Barney's paper or familiar with just the decomposition for general links. Yeah. Now the first part, this is all of the content of the first part. Now we move on to the second part. In the second part, we will systematically consider the decomposition of Brunnian links using satellite sum and satellite tie, and we will give a canonical decomposition of Brunnian links. Yeah. The topic sentence in this part is as follows. Yeah. The building blocks in a class of Brunnian links are either 2-to-1 torus links, or called hopeful N links, or hyperbolic Brunnian links, or hyperbolic Brunnian links in unlinked complements. Yeah. The term building blocks, its meaning is that these three kinds of Brunnian links generate all Brunnian links by satellite sum and satellite tie. Yeah. Now we first consider the following one. Yeah. Before give
Excuse me, can I see building blocks again? So toric, and what else? Hyperbolic. Okay, and hyperbolic. So is 3 a partial case of 2? No?
No, not at all.
Okay, I think you can study a lot, well, almost everything by using our methods with Zsuzsanna and Sarah. And actually, one more question. We can do quite a lot. So we can create 3 manifolds. And actually, in the paper by Manolescu and Piccirillo, they created lots of
manifolds which are homotopically S3, so they were S4 maybe, and they were trying to disprove the Poincare conjecture. And you see, I'm pretty sure that Brunnian links are underestimating in construction of such nice examples. So just look through the paper by Manolescu and Piccirillo.
Okay. Yeah. 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 But yeah, our second part have three have three small parts. Yeah. The first part is the geometric classification for Brunnian links. Recall the famous geometric classification for knots, which is proved by Thurston, that every knot is exactly in one of the three classes, torus knots, hyperbolic knots, and satellite knots. Yeah. This part resemble famous Thurston's result. Yeah. But the main task in this part is to discuss what is a Safford fibered Brunnian link. Yeah. Firstly, we will show why 2-2 and torus links are special. Yeah. The Brunnian links with essential annulus joining different boundary components in their complement space are 2-2 and torus links. Yeah. Yeah, we will call the 2-2 and torus links to be Hopf N-link. Yeah. We note that Hopf N-link has a cipher fibered complement, where once n is a non-zero integer. Yeah, and the Hopf N-links are of course S prime and untied because the complement spaces are toroidal. Yeah. Simply speaking, yeah. If a Brunnian link is Safford fibered, then this Brunnian link must be Hopf N-link for some non-zero integer n. Yeah. Now we can state our geometric classification theorem for Brunnian links. Yeah. If a Brunnian link L is S prime, untied, and not a Hopf N-link, then S3 minus L has a hyperbolic structure. In other words, L is hyperbolic. Yeah. Yeah. Or in other words, if a Brunnian link L is S prime and untied, then L is either a Hopf N-link or a hyperbolic link. Yeah. This is from this proposition and the famous Thurston's hyperbolization theorem. Yeah, I think, yeah. This is just a classification. Yeah. We will consider decomposition later. Yeah. Why we consider decomposition? Because we want to give a canonical decomposition for Brunnian links if the link is not S prime or untied. Yeah. Yeah. That would be deeper and more general. Yeah.
May I see a proposition 213 once more? So
classification, right? Yeah.
So it's Brunnian in S3 minus U, then in the complement. Okay, no essential annulus.
I skipped this proposition. I just talk about.
Yes, and one more remark. I think it may be of a great use. in many situations. So we are interested in getting some additional structure for studying links. And so we need, for example, a full torus somewhere. But if we have just a link, we can get a satellite Brunnian link. And if we have a satellite Brunnian links, then we have lots of annuli. And having lots of annuli, we certainly have lots of parities, indices, and whatever. And I invite you to join our conversations on Saturdays and Sundays. So we are discussing what we are doing now.
Oh, okay.
I think Brunnian links will help a lot.
Okay. Yeah. Annulus, I think annulus is not too many. Annulus will not be too many annually. Will not be too many.
No. I mean, if we just make each component can become, each component can become. We can make trivial components out of non-trivial ones, and making that we can create a source of tori. Okay.
Oh, okay. Yeah. Yeah. Here. Yeah. The sentence is a little a bit wordy. Yeah, because the condition is that essential annulus joining different boundary components. Yeah. If there exists such annulus, then the link can only be two-to-one torus links. So yeah, the sentence is a bit wordy. Yeah, but we are more interested in the geometric decomposition. Yeah, actually, geometric decomposition will be more interesting. Yeah. For geometric decomposition of general links, we should recall Badeni's paper, frequently cited paper, where Badeni describes formalism for the JSJ decomposition of link complements. Actually, he constructed two graphs associated to a link. One is called a JSJ graph. One is called a companionship graph. Yeah. More or less, it is like the graph for general three-manifold representing its JSJ decomposition. Yeah, but here each vertex.
By the way, have you presented your talk at the seminar by Kaufman and Fenn? I think you can, so people can watch your talk. You can invite Jaco or other people.
Sorry, please.
So there is a nice seminar by Lou Kaufman and Roger
I know.
Fenn.
Yeah, I know.
Have you given a talk there?
I always listen their talks. Yeah, listen their seminars.
Just go ahead. Just give a talk there.
Okay, thank you. Yeah, maybe I can have a try. Yeah, maybe okay. Maybe I can ask Professor Kaufman or Professor Roger Fenn. Yeah. Okay. Okay. Now let's see this part. Yeah. I hope someone would feel this part interesting. Yeah. Yeah. Firstly, I want to talk a bit about the general companionship graph and the JSJ graph for general links defined by Badeni. Yeah. Briefly speaking, the companionship graph is a partially directed tree with each edge labeled by a JSJ decomposition torus, and each vertex labeled by a link whose complement is homeomorphic to the corresponding JSJ piece. Yeah. And such a graph is a labeled graph. It's called the companionship graph. This graph with labels forgotten, yeah, with labels discarded is the JSJ graph. Gesture graph is just a graph. Yeah, with the labels are discarded. Yeah. Now we will characterize these two graphs for Brunnians. Yeah, it have a beautiful beautiful figure actually. Yeah. Firstly, we will consider the gesture graph that is with no labels. Yeah, just the graph itself. Yeah, for Brunnians. Yeah. Now we will define a kind of a tree, a partially directed tree. The figure is like this. Canonical. Yeah. A figure is like an example is like this. Yeah. A partially directed tree is a planting tree if all of its vertices and directed edges form a disjoint union of rooted trees. 1, 2, 3. Yeah. And the endpoints of each non-directed edges are roots. Yeah. These are non-directed edges. Yeah. Then we will get such a tree called a planting tree. Yeah. Actually, I call it a planting tree because the picture is somehow like a garden. Yeah, and you plant some trees along some paths. Yeah. Yeah. Then the result is the JSJ graph of a Brunnian link is a planting tree. Yeah. Now, if we explain it more detailedly, yeah, we will explain the companionship graph. I mean that I will describe what links should these vertices labels. Yeah. Yeah. In the companionship graph of a Brunnian link, yeah, each leaf means the endpoint here. Yeah. The edgemost. Yeah. Outermost edges. Each leaf is labeled by a knot, and each vertex, neither a leaf nor a root, is labeled by a knot generating link. This is defined by botany. Yeah, but such a tree is just a gesture graph for a knot. Yeah, this result is in botany's paper. Yeah. The first class explains each tree. Yeah, what is each tree? Yeah. Now, the directed edges terminating to a vertex correspond together to a trivial sublink of the link labeling this vertex. Yeah, this is also an explanation of each directed tree. Yeah, each.
What is KGL?
Not generating link. This is the term defined by botany. Yeah.
Oh, okay.
Yeah, but they are not really important for us because these are all written in botany's paper. Yeah, this gesture graphs are just the gesture graph for the for the knots. Yeah, for the companion knots. Yeah. Moreover, yeah, as will be shown at the end of this section. Yeah. But of course, we will not show the proofs. We have the following. Yeah. Each root, yeah, we need to explain what the root represents. Yeah, each root is labeled by either a hopful unlink, a hyperbolic link, or a hyperbolic Brunnian link. Sorry, a hyperbolic Brunnian link or a hyperbolic Brunnian link in an unlinked complement. Yeah. If this root, there is no tree. There's no any rooted tree grown from this root. Yeah, this root is labeled either by hopful unlink or a hyperbolic Brunnian link. Yeah, if there are some rooted trees grown from this root, yeah, then this root is labeled by a hyperbolic Brunnian link in unlinked complement. Inaccurate. If the pattern here is L1 and UL, L1 in the unlinked complement UL in S3, and UL is a complement of the unlinked small l. Yeah. Then the root is labeled by the link L1 destroy the union with LL. Yeah. And conversely, yeah, companionship graphs satisfying the above three properties correspond bijectively to Brunnian links. Yeah. If there is if this part is a bit wordy, it's okay, because we will show a canonical decomposition for Brunnian links, yeah, later, which is simpler than the J-straight graph or companionship graph. Now we move on to our canonical decomposition for Brunnian links. We call it a Brunnian tree arrow structure. It will be simpler than the J-straight graph. Yeah. Now let's give the definition of a tree arrow structure. Yeah, a tree arrow structure actually, I call it a tree arrow structure because there is a tree, non-directed tree, yeah, on the plan, and some arrows go upward. Yeah, the union, all of them consist the tree arrow structure. Yeah, actually the tree is actually the satellite sum composition. Yeah, tree. Yeah, and these arrows are actually just the what is it's just what is used in the definition of satellite type. Yeah, let's precisely explain it now. If a link is a satellite sum of certain links, we draw the tree structure of the satellite sum expressed in terms of the links and the removed components on a horizontal plane. And then, if a factor in the tree, if some factor in a tree is a satellite type, yeah, we make the following replacement. We then replace the satellite type factor by their representation in the definition of satellite type. Yeah, but the arrows are drawn upward like this. Yeah, we call such representation a tree arrow structure. Yeah. Now, moreover, if each factor with no arrow is either a hyperbolic Brunnian link or a hopeful n-link, like L5 and L4, yeah, and each link in the satellite pattern, in the S pattern, is a hyperbolic Brunnian link in unlinked complement. Yeah, like this, right? Yeah. Then we call this representation a Brunnian tree arrow structure. Yeah. Actually, this is the this is our canonical decomposition for Brunnian link. Yeah. The result is like this. Brunnian tree arrow structures correspond bijectively to Brunnian links. Yeah. I mean, for each Brunnian link, you can make such a canonical decomposition. Yeah, and when you have some hyperbolic Brunnian links and hopeful n-links and some hyperbolic Brunnian links in unlinked components, and you pick any knot types here. Yeah, several knot types here. Then you can form Brunnian link uniquely. Yeah, use such a tree arrow structure. Yeah. What is the relationship between this canonical decomposition and the canonical structure and the J-straight decomposition, J-straight graph? Actually, Brunnian tree arrow structure is essentially the companionship graph, but with each maximal rooted tree replaced by its representative knots. Yeah, I mean that the relationship between this picture and this picture is actually this is actually a J-straight decomposition, the J-straight graph for the knot, for companion knot. Yeah. Now we will not show how this knot is decomposed by satellite operations. Yeah, we will just abbreviate, use the companion knot itself. Yeah, these three are just the geometry graph for the companion knots, and we will not give this decomposition of these knots. We will only give the give the companion knot, the 5 companion knot is themselves. Yeah. This is the our main result in this paper, actually. As a result, we recall what we said earlier. Yeah, the topic sentence in this part is that the building blocks in a class of Brunnian links are either hopeful n links or hopeful n links, hyperbolic Brunnian links, or hyperbolic Brunnian links in unlinked complements. Yeah. In that they generate all Brunnian links by satellite sum and satellite tie. Yeah. The problem is, what is a natural problem? A natural problem is that what is the third thing? Yeah. Is this a good thing? Yeah. Is this easy to study? Yeah. Actually, we are not satisfied with such a result because we don't like this one. We don't like the third case. Yeah. This leads to our third part. We will reduce such thing into hyperbolic Brunnian links in S3. Yeah. Our third part is untying Brunnian links. Yeah. The topic sentence is that we define an operation to reduce a Brunnian link in an unlinked complement into a new Brunnian link in S3. Yeah. Why we need to do this? Because Brunnian links in unlinked complements is not a good object because those might be too diverse generally. Yeah, let's have a look at one example. Yeah, consider the Brunnian link here. This is a Brunnian link. Yeah, and we consider the red circles in the right figure. Yeah, C1, C2, C3, C4. Yeah, then L is also Brunnian in the following unlinked complement space. For example, S3 minus each one components, S3 minus each two any two components, S3 minus any 3 components, and S3 minus all of the 4 components, and so on. Actually, we may even twist or tie a knot here of any type at the middle part of C4 here. Yeah, you can twist the red circle here, or even tie a knot here. Yeah, the result then L will be also Brunnian, will be still Brunnian in the complement space. Yeah. So, yeah, we therefore obtain infinitely many distinct Brunnian links in the Brunnian links in unlinked complement space, in unlinked complements from this one link L. So compared with Brunnian links in S3, Brunnian links in unlinked components are generally too diverse. Yeah, so we don't like this thing. Yeah. Now we give the definition to reduce this one into a new Brunnian link in S3. The operation is called untie. Yeah. Let L be a Brunnian link in S3, and T be a torus in a complement space S3 minus L, which bounds a solid torus V such that L is contained in V. The whole L is contained in V. Yeah. We say untie T for L, or say we perform untying T for L. If we re-embed V into S3 in the unknotted way by a map H such that the longitude of V is mapped to the meridian circle of S3 minus interior of HV. This is just this sentence is used to make the definition uniquely well defined. So we make the untie, we make a re-embedding in an unknotted way. Yeah, and we need to use a standard way to avoid the twist of the solid torus. So this sentence is gives a standard way. Yeah. And there are two cases, yeah, for untying. Yeah, we should take the HOL destroyed union with C as a resulting link if HOL is trivial in S3. Yeah, here C is the core of the solid torus, which is the complement of HV. Otherwise, yeah. If HL is non-trivial in S3, we just take HL. Yeah. It is straightforward to show that the resulting link is Brunnian. Yeah. Untying inessential torus gives just the original link. Yeah. So it is not interesting. So we only focus on essential torus. Yeah. In other words, we actually do something like this. Satellite tie is an operation from the left to the right, and the untie is an operation from the right to the left. Yeah. The red part is essential, knotted essential torus in the complement space of the black link. Yeah. And we re-embed this red solid torus into S3 in an unknotted way, which should be uniquely well defined if we fix which should be the longitude and which should be the meridian. Yeah, then we get a new link in S3. Yeah. But this link can be trivial or non-trivial. If non-trivial, just take this link. If trivial, we take this link and take the union of this link and the core of the complement space to get a new link. Yeah, this is the definition of untying. Yeah. Now, suppose we have a general Brunnian link, and the collection of the 5 companions is like is as follows. 3 questions arise. Yeah. First, is the type of untying invariant under the change of order? I mean, the type means type 1 or type 0. Yeah. Yeah. And the second question is, after untying T1, does T2 must remain essential? Yeah. The third question is, after untying all 5 companions of L, is the resulting link untied? Yeah. The answers are no, no, no. Yeah. We have examples to show them, but I don't want to talk.
May I see the third question?
Okay, okay. The third question, yeah. This is all the 5 companions of a Brunnian link. We can untie them one by one.
Okay.
Then we will ask, is the result link untied? No. Yeah. A counter example is like this, but I will not show it in detail now. I only want to say that so the untying operation is somehow not that easy, not that simple. Yeah, there are some complicated phenomena. Yeah, actually, yeah. But we can generally say that here, yeah, we can generally say that study of Brunnian links in unlinked complements can always be reduced to the study of Brunnian links in S3. because of the following proposition. Yeah, for every Brunnian link L in an unlinked component UN, there always exists an embedding H from the unlinked complement to S3. Yeah, so that S3 minus HUN is a regular neighborhood of unlink, and HL is Brunnian in S3. Yeah. Actually, I mean that if you draw a Brunnian link in an unlinked complement, you can always draw it in S3 because unlinked complement can be drawn in S3. But there is always a way to draw it so that L is always L is still Brunnian in S3. Yeah. So study of Brunnian links in unlinked complements can be reduced to that in S3. Yeah.
I think you can also discuss it with Eiji Ogasa. So he's trying to use something like manifolds with boundaries and links and manifolds with boundaries to study just classical links in S3. In particular, he's trying to study virtual knot theory in order to understand classical knot theory. I'm pretty sure that Brunnian links will have a great source of examples.
Oh. So I want to first give a summary. Yeah. Here. This is also the summary. This is a summary of the third part, also a summary of the whole talk. Yeah. On the whole, given a Brunnian link in an unlinked complement, one can always untie it.
Professor Yao has come. Excuse me. So please give
Yao 老师您好。I think Baishang, you can repeat a little bit, maybe the main summary of the whole work, if you don't mind.
I think I've finished my talk.
Well, but okay, I think you can make a summary of everything what's happened, what's happening before.
Okay. Firstly, here. Yeah. So what is a Brunnian link? Yeah. A link L of n components where n is bigger than 1 in S3 is Brunnian if it satisfies the following properties. Every sublink with n-1 components is trivial, and L itself is non-trivial. Yeah. So Brunnian links are the almost trivial links in S3. They are important because they can be somehow viewed as the building blocks of general links, in the sense that for any link, the non-trivial sublinks with the least number of components are either knots or Brunnian links. Yeah. In our work, actually, we give new names to special kind of satellite operations for Brunnian link. One is called a satellite sum, and the other is called a satellite tie. Yeah. Satellite sum is defined by using the unknotted essential torus to compose a new Brunnian link from given Brunnian link. Yeah. And the satellite tie is defined by using knotted essential torus. Yeah, knotted essential torus to construct new Brunnian links from Brunnian links in some unlinked complement space. Yeah, which means that the complement of some unlinks. Yeah, these two kind of satellite operations have good properties, such as some uniqueness and existence result, when restricted to Brunnian links. Yeah, and use these two, use the decomposition direction of satellite sum and satellite tie. We give the canonical, we give the geometric classification result for Brunnian links, which resembles the famous geometric classification for knots. Yeah, which states that the main theorem states that if Brunnian link L is S prime, which means it is not a satellite sum, and untied, which means it is not a satellite tie. And then if L is not a 2-to-1 torus link, or called a hopeful n-link, then S3 minus L has a hyperbolic structure. Yeah, this is the geometric classification theorem for Brunnian links. Yeah, we can example, we can compare it with the famous theorem by certain states that each knot is either a satellite knot, it's exactly one of the three classes: satellite, torus knots, hyperbolic knots, and satellite knots. Yeah, and after the geometric classification for Brunnian links, we go on to give a more general result about a canonical geometric decomposition for general Brunnian links. Yeah, which is here. Yeah. We define such a graph. Yeah, such a graph called a tree arrow structure, which yeah, a tree arrow structure. Here each link here is either hopeful n-link, or say 2-to-1 torus link, or a hyperbolic Brunnian link. And here is some hyperbolic Brunnian links in unlinked complement space, and here is the representation of satellite tie. Yeah, such thing together forms such things together form a tree arrow structure. And our canonical decomposition theorem for Brunnian link is that Brunnian tree arrow structures correspond bijectively to Brunnian links. Yeah, and then the basic building blocks for, in a geometric decomposition sense, yeah, the building blocks of Brunnian in a class of Brunnian links are just 2-to-1 torus links, hyperbolic Brunnian links, or hyperbolic Brunnian links in unlinked complements. Yeah, in that they generate all Brunnian links by satellite time and satellite tie. And the second case and the third case are totally different. Yeah, but the third part are generally some too diverse objects. Yeah, it's not good. We are not satisfied with the occurrence of such thing. So lastly we define an operation called untying. Yeah, the operation untying can reduce this third kind of this third type links. Sorry, this is the third one into the second the third one into the second one. Now, so we can draw the whole conclusion of this talk here now. On the whole, given a Brunnian link in an unlinked complement, one can always untie it into untied, and then decompose it into S prime factors in finite steps. Then the resulted links are untied and S primes. Because we decomposed it, so one link is generally decomposed into several links. So we say the resulted links are untied and S prime. Yeah. In a word, well, we can say that the 2-to-1 torus link, or called a hopeful n-link, and hyperbolic Brunnian links are the building blocks in the class of Brunnian links, in that they generate all Brunnian links by satellite sum and satellite tie. Yeah.
How constructive is that? What about algorithms? So is it only theoretically constructive, or is it possible to write a program?
Of course, just algorithm, but actually just directly we can do this.
And so can we teach our computer how to do that?
Oh, we can just direct do this, I think. Yeah, if we have some 2-to-1 torus links and some hyperbolic Brunnian links, yeah, and we can firstly we can find many hyperbolic Brunnian links in unlinked complement space, such that like in this figure. Yeah, we find some unlinked in the complement space. We find some unknotted components, unknots, and then we just use this trial structure to make a composition.
So in 3D topology, there are some algorithms. So we try to construct some surfaces, say like Seifert surfaces, and try to look at their intersection and try to minimize them. So there is a general algorithm, say in Matveyev's book, and after that they can be simplified. So for knot theory, the simplification algorithm can work very quickly if we deal with grid diagrams of knots. So actually, there are not only theoretically but practically effective algorithms for knots. So now, what about Brunnian links?
Okay. I can explain this question very clear, I think. Yeah. Actually, in this sentence, I say that two torus links and hyperbolic Brunnian links are the building blocks in a class of Brunnian links, in that they generate all Brunnian links by satellite sum and satellite tie. It means that if we have some two torus links and hyperbolic Brunnian links, we can just put them into these parts and find and take any knot types here, and we will get the general links. Yeah, this is directly. But what you ask is really the converse part direction, the decomposition part. Yeah. What you really ask is that given a general link, how can we get such a decomposition? I think, right?
No. I'm asking, given a Brunnian link, we are interested in tori and essential tori in the complement. For example, when we look for spheres, for example, for the composition of classical links into prime components, it's very effective if we deal with grid diagrams. But what about tori? Maybe it can also be effective.
So if we want to find, is there any essential torus in the complement space of a Brunnian link, right? Yeah, this question. Yeah. This is the main content of my next paper.
Okay, it would be great. Yeah, it would be great to compare it, for example, with Denikov's paper about unknot recognition.
Okay. I only know some work by Rubinstein. I don't know your.
No. I mean, well, okay. I will send it separately to you. Thank you.
Okay, thank you. And I have a last question here. Yeah. The following problem is basic but seems challenging. Yeah. Given a Brunnian link, find or classify all the unlinks not in intersecting L, such that L is Brunnian in their complements. Yeah. This question is motivated by this example. Yeah. This is a Brunnian link in S3, but it is also Brunnian in the complement of in the complement space of the red unlink. Yeah. That's all. Thank you.
Okay, thank you very much for a very nice talk. Dear colleagues, please, your questions. Mute your microphones if you. Comments, maybe remarks. Well, okay, we have got quite a lot of questions during the talk. So let's thank the speaker again for a very good. Sandra, do you have a question?
No, thank you. Okay, thanks. Thank you.
Oh, so let me have a look at your comments on the chat line. I
Oh yeah,
cannot,
sure.
Parodies. What is known about the Brunnian three manifolds surface along Brunnian links? I'm not sure about your question. Yeah.
Yeah, in Friedman's group and in some other groups where people are trying to tackle the smooth 4D Poincare conjecture, there are some methods of constructing homotopical force sphere by using surgeries. By using surgeries of some knots or links which are very similar to the unknot or the unlink. And if we say something very similar to unknot and unlink, Brunnian link should definitely play a very good role.
JCZHS.
Integral homology spheres.
Oh, sorry. What homology sphere? Zero.
Integral homology sphere, Z.
Oh.
Z. I mean, not rational.
Okay.
Okay. Without torsion.
Create a Brunnian link out of it. We will have many, because you have lots of. Oh, okay. Thank you. Okay.
Okay. Thank you. Any more questions or comments? Okay, thank you very much.
Thank you.
And that's all for today.